Okay, as we continue, the magnitude of the secondary consolidation can be calculated as, so we have here the formula to compute for the secondary settlement for the settlement for secondary consolidation. So basically, you have this equation, and this C of alpha prime is equal to C of alpha all over 1 plus E sub p. Take note that E sub p is the void ratio at the end of primary consolidation. So we have here, and of course, H is the thickness of the clay layer. So we have here a figure showing the variations of A with log T under a given load increment and definition of the secondary consolidation index. So the general magnitude of C sub alpha prime as observed in various natural deposits are as follows. So we have here the different magnitude of the value for alpha C sub alpha prime for overconsolidated clay, that is 0.001 or less, for normally consolidated clay, that is 0.005 to 0.03, for organic soil, that is 0.04 or more. So according to Mercery and Godlewski, compile the ratio of C sub alpha prime over C sub C for a number of natural clays. From this study, it appears that C sub alpha prime over C sub C for inorganic clay and silt is approximately 0.04 to positive or negative 0.01. For organic clay and silt, the ratio is approximately equal to 0.05 positive or negative 0.01. And for peat, that is approximately 0.075 positive or negative 0.01. For secondary consolidation settlement, it is more important than primary consolidation in organic and highly compressible inorganic soil. In overconsolidated inorganic clay, the secondary compression index is very small and of less practical significance. So we have here a sample problem. For a normally consolidated clay in the field, the following values are given. For thickness of clay layer, that is 2.6 meters. For the void ratio, E sub O is 0.8. Compression index E sub C is 0.28. Average effective pressure on the clay layer, sigma sub O prime, is 127 kilonewton per meter squared. We have delta sigma sub O, delta sigma prime is equal to 46.5 kilonewton per meter squared, and the secondary compression index C sub alpha is 0.02. So you're going to compute for the total consolidation settlement of the clay layer 5 years after the completion of the primary consolidation settlement. You have to take note that time for completion of primary settlement is 1.5 years. So our C sub alpha prime is, of course, C sub alpha all over 1 plus E sub p. And the value for E sub p can be calculated using this equation. E sub p is E sub 0 minus delta E sub primary. So delta E is equal to C sub C log of this expression, which is equivalent now to 0.28 log of 127 plus 46.5 over 126, and that gives us the change in void ratio is equal to 0.038. And for primary consolidation, this is the formula. We substitute our values for the parameters. It gives us 54.9 mm. So it is given that E sub O is 0.8. So therefore, our E sub P is 0.8 minus 0.038. It gives us 0.762. And C sub alpha prime is equal to 0.02 all over 1 plus 0.762, which gives us 0.011. So we move on now to time rate consolidation. Okay, we move on to time rate of consolidation. So for the total settlement caused by primary consolidation resulting from an increase in the stress on a soil layer can be calculated using these equations. So we have here 3 equations for us to compute for the total settlement caused by the primary consolidation as resulting from an increase in the stress on the soil layer. So, however, they do not provide any information regarding the rate of consolidation, of primary consolidation. According to Terzaghi, he proposed the first theory to consider the rate of one-dimensional consolidation for saturated clay soil. So the mathematical derivations are based on the following assumptions. So the clay water system is homogeneous, of course, basically. Since this is one-dimensional, saturation is complete, compressibility of water is negligible, compressibility of soil grains is negligible, and the flow of water is in one direction only, that is the direction of compression, and Darcys Law is valid. Of course, we know that Darcys Law is basically involves the discharge velocity and of course the permeability coefficient. So the basic differential equation of Darcys consolidation theory expressed in this form. So this can be solved with the following boundary conditions. So we have here the conditions, boundary conditions for us to solve for the Darcys consolidation theory. So basically the solution yields, so if we try to apply the boundary conditions, our U, which is now our, this can be, our U now would be equivalent to this expression. So our m, small m is an integer, capital M is equal to this expression, and U sub O is the initial excess for water pressure. And the time factor now is equivalent to this equation. So the time factor is non-dimensional number. So because consolidation progresses by dissipation of excess pore water pressure, the degree of consolidation at a distance z at any time t is given by this expression. So this one now is the degree of consolidation at any distance z at any time. So it is given by this expression, and U sub z is the excess pore water pressure at time t. So we have here a figure, a variation of U sub z with t sub v and z all over h sub dr. So we just have to, we need the value of degree of consolidation. And of course, you can have the value for the time factor and the ratio between z all over h sub dr. So the average degree of consolidation for the entire depth of the clay layer at any time is given by this expression. So the average degree of consolidation at any depth of the clay layer is equal to settlement of the clay layer at time t all over the ultimate settlement of the layer from primary consolidation. And that is now equivalent to this expression. So the variation of the degree of consolidation with the dimensional time factor T sub v is given in the figure 11.26, which represents the case where U sub O is the same rate for the entire depth of consolidating layer. So we have here the variation now of the degree of consolidation with time factor T sub v and U sub O constant with depth. So you have the time factor and versus the average degree of consolidation. So the values of the time factor and the corresponding average degrees of consolidation for the case presented in 11.26 was approximated by the following simple relationship. So we have here the relationship as presented on figure 11.26. So we have table 11.7 gives the variation of T sub v of the time factor with the degree of consolidation mu. So according to Zivaram, Schwamme gave the following equation of U varying from 0 to 100%. So this is the theory of Zivaram and Schwamme. So we have here now the variations of the time factor with our degree of consolidation. It is presented in this table 11.7. So we have here a sample problem. For normally consolidated laboratory clay specimen grade on both sides, the following are given. So we're given with these parameters. Determine the hydraulic conductivity of the clay for the loading range. How long in days will it take for a 1.8 meter clay layer in the field drained on one side to reach 60% consolidation? So for our solution, we have the coefficient of compressibility. So we have to take note of this. M sub v is given with this expression. Delta E is equal to 0.2. And the change in sigma sub prime is 150 kilonewton per meter squared. Of course, E sub AB is equivalent to 1.0. We just have to substitute this to our equations presented a while ago. So therefore, our coefficient of compressibility is equal now to 6.55 times 10 to the negative 4 m squared per kilonewton. And from our table 11.7, our U is 50%, our T sub V is 0.197. So we can have now your C sub V, which is equivalent to 1.53 times 10 to the negative 4 meters squared per meter. And our K, substitute the given values. So it gives us 95.3 times 10 to the negative 7 centimeter per meter. And our time factor at 60%, we have this equation. And from table 11.7, when U is 60%, our time factor is 0.286. So simply have to substitute your time factor to this equation. So for 60%, degree of consolidation, so it gives us 60,565 minute or 42.06 days. So we move on now to coefficient of consolidation. So the coefficient of consolidation, C sub V, generally decreases as the liquid limit of soil increases. So the range of variation of C sub V, which is our coefficient of consolidation for a given liquid limit of soil, is wide. So for this one, for the given load increment on a specimen, we have two graphical methods commonly used to determine our coefficient of consolidation C sub V. These are from laboratory one-dimensional consolidation test. So the first is the logarithm of time method, which was proposed by Casagrande and Fadum, and the other is the square root of time method that was given by Taylor. So more recently, the least two other methods were proposed. So they are the hyperbola method by Prakash and the early stage log T, which is a theory of Robinson and Alam. So the general procedure for obtaining the coefficient of consolidation C sub V are described. So we have here the first one. So this is the logarithm of time method. So we have here the procedure on how to plot our figure using the logarithm of time method. So we're going to follow that one. So this is now the logarithm method for determining the coefficient of consolidation. And the square root of time method, so this is the procedure in obtaining the figure using the square root of time method to determine our coefficient of consolidation. So this is now the figure showing to us the square root of time fitting method. So HDR is determined in a manner similar manner to that of the logarithm of time method. So the third one is the hyperbola method. So in this figure, you are recommended with this procedure so that you can calculate your coefficient of consolidation. So this is now the figure for the hyperbola method for the determination of C sub V. And the hyperbola method is fairly simple to use and it gives good result for our degree of consolidation, which is 60 to 90%. So we have now the early stage log T method. So this is an extension of the logarithm of method. It is based on the specimen deformation against log of T time plot as shown in this figure. So basically, this is the corresponding coefficient of consolidation for early stage log of T method. So this is the figure for the early stage log T method. So we have plotted here our time with respect to versus our deformation. And we have here a table 11.8 comparison of C sub B obtained from various methods. This is dependent on the given soil sample. So still a continuation for the coefficient of consolidation.